So what we're going to discover in this video is that evaluating some line integrals in a vector field under certain circumstances, as we go from one point to another, the amount of work done will be the same irrespective of the pathway that we take to go from one point to another. For example, what if we want to evaluate the following line integral under this vector field f, which is the vector 2x comma 3y squared, and let's say the curve will be a straight curve. Let's say the curve we want to go along starts at 0, 0 and ends at 1, 2, and it's this straight line to get from 0, 0 to 1, 2. And we'll call this curve curve sub 1. So we want to find the line integral f dot dr, which we know will represent the work done along this curve as we go in this particular vector field. Well, what we've often done is to try to parameterize in terms of t, so we can make this integral expression turn into a single variable evaluation. So let's parameterize this straight line curve going from 0, 0 to 1, 2. No doubt you recognize that as a little line segment or piece of the graph y equals 2x, but we're going to parameterize that. So we'll let x equals t, and we'll let y equal 2t as t goes from 0 to 1, which corresponds to x going from 0 to 1. So clearly that means that dx equals dt and dy equals 2 dt. So when we look at the line integral structure, which is f dot dr, here's the vector field f. We're going to dot it with dr, which is the differential expressions in vector form, dx dy, and we have a familiar line integral in terms of x and y along curve 1. But as we said, we parameterize to make the evaluation easier. So what would 2x dx look like if we put in the parametrics? Well, x is t, so that would be 2t, and dx is dt, that would be 2t dt, easy. But when we have 3y squared dy, let's see now, y was 2t, so y squared would be 4t squared times 3, 12t squared. And of course, we also want to put the differential dy, but this time dy is 2 dt, since y was equal to 2t. So that's why we have this 2 dt expression here. And notice with both pieces in terms of t, both these integrals, we have the limits of integration t going from 0 to 1 in both cases. So the integral of 2t is t squared. The integral of 12t squared times 2, or 24t squared, is 8t cubed. And when we use the fundamental theorem of calculus, we get an answer of 9. But the interesting thing is, what if we wanted to get from 0, 0 to the point 1, 2, we wanted to take a different pathway. Instead of going the most direct way, from 0, 0 straight across to the point 1, 2, what if we instead started at 0, 0, then went to 1, 0, and then from 1, 0, went upwards 2 units to the point 1, 2. So we're going to evaluate that. We're going to call this pathway from 0, 0 all the way along to 1, 0, and then from 1, 0 to the point 1, 2. We're going to call that curve C sub 2. And it's, of course, made up of 2 straight pieces. Now, we're going to parameterize, but this time we'll have to parameterize in 2 separate pieces because we have 2 distinct algebraic expressions for these little line segments along, in this case, the x-axis, and then going up from there. So let's parameterize the first segment by letting x equal t. And you'll notice if x is t and x goes from 0 to 1, then t has to go from 0 to 1. And dx will equal dt. But notice, as we go from 0, 0 to 1, 0, is y changing? Not at all. We're staying at this level. So y equals 0, which of course means that dy equals 0. We're also going to parameterize the second segment from 1, 0 to the point 1, 2. If we let, in this case, y equal t, y is going to vary from 1 to 2, so t is going to vary from, not from 1 to 2, but from 0 to 2. And we will let x equal 1 because x is not changing in this case. X is fixed at 1 as we go along this segment. So that means that dx equals 0, dy equals dt, because we let y equal t on the interval from 0 to 2. And we're going to refer to the first segment, this horizontal piece, as curve sub 3, and this vertical piece from 1, 0 to 1, 2. We're going to call that curve sub 4. So again, going along this curve, all taken together, we called it curve sub 2. Now we're going to break it up into the horizontal piece. We call it C sub 3, and the vertical piece we'll call it C sub 4. we make our substitutions again. Instead of 2x 3y squared, we're going to put 2t. And since y was 0, 3 times 0 squared would give us a 0 here, as that y component of the vector field. Dotted with the differential vector, used to be dx dy, but now we have x equals t, so it'll be dt, and since y is 0, we'll have 0 here. If you evaluate that from 0 to 1, as was the first range of values, we get an answer of 1. Now as we evaluate along this vertical piece, which we call C sub 4, notice that the vector field turns into, let's see now, x is 1, so 2 times x, 2 times 1 is 2, 3y squared, but y was t, so you have 3t squared. X isn't changing, so the dx equals 0, and of course y equaled t, so dy equals dt, and we have this expression. And we evaluate that. It go from 0 to 2, which is what we had for the second parameterization, 3t squared dt. Fundamental theorem, we get 8. But notice something interesting. What did we get before when we went from 0, 0 all the way to 1, 2 in the most direct approach? Didn't we get an answer of 9? Well, in that regard, with an answer of 9, you can see that 1 plus 8 gives you that answer of 9. So it doesn't matter if we went from 0, 0 to 1, 2, or instead we went from 0, 0 to 1, 0, and then from there, at 1, 0, went up to 1, 2, we got the same work done, which is 9. And the reason why is because we're in a very special kind of field, and we're in a very special kind of region, which we'll talk about in a moment with these diagrams. If you look at the function phi x of y equals x squared plus y cubed, let's find del phi. What does your result imply about the force field, 2x, 3y squared? Well, del phi, as you recall when you studied partial differentiation, del refers to the partial derivatives of phi with respect to x, partial derivative phi with respect to y. So that's interesting that del phi, this vector, which is partial with respect to x, partial with respect to y, that is the exact same thing we were using before as our vector field. In fact, this is a very special situation. It's not a coincidence that whatever pathway you take to get from one point to another, as you evaluate the line integral, that you get the same answer. The reason that happens is because this particular vector field is a conservative vector field. And there are easy ways to test and to make sure that you have a conservative vector field, but we're just here to demonstrate a neat trick that you can use to evaluate line integrals when you are in a conservative vector field. In fact, we can prove that if a force field F is conservative, then the work that the field performs on a particle that moves from P to Q does not depend on the particular path C that the particle follows. And that's true as long as the domain D of the vector field is connected. A domain D of a vector field is said to be connected if any 2 points in that domain D can be joined by some piecewise smooth curve that lies entirely in D. So this region, although it's a little bent in this direction, if I was at a point down here and I wanted to get to a point over here, I could create a smooth curve that would get me there in that open region D. And that's what we mean by a connected domain. The vector fields, rather, that's called or described as being connected. Now let's go back to the situation we dealt with earlier. We now know that phi xy, when we take del of that function phi, we get the vector field. But let's stop for a moment and evaluate phi at our terminal point and at our initial point in the first way we got to do things. The first problem we did, we started at the origin, went directly to our terminal point 1, 2. But let's plug 1, 2 into phi, and let's plug 0, 0 into phi. What do you get? Well, of course, 1 squared plus 2 cubed is 8, is 8 plus 1. And 0 squared plus 0 cubed is 0. Fundamental theorem is what it appears to be here, same structure. We get an answer of 9. Now, what if you evaluate in the other pathway that we had before? We called it C2. If we went from 0, 0 to 1, 0, then from 1, 0 to 1, 2, if you evaluated one piece at a time, what if you evaluated at phi 1, 0, this terminal point with the first horizontal segment minus phi 0, 0, and then you added to that phi 1, 2, your terminal point, minus phi 1, 0. Well, if you did those calculations, it's interesting, you get 1 minus 0 plus 9 minus 1 in the final evaluation, or 9. So again, we get the same answer of 9, but notice we didn't have to do any integration. We just instead used phi itself. And as I mentioned earlier, this is referred to as the fundamental theorem of line integrals. Even in the beginning when we looked at this structure, it kind of had the feel of fundamental theorem of calculus. And it's exactly what's going on, and we're going to prove that in a moment. These results seem to imply that a fundamental theorem of line integrals in conservative vector fields exists. And the following theorem provides us with a simpler way to evaluate line integrals under these circumstances where you have a conservative vector field. So the theorem goes like this. Suppose that big F of xy equals little f xyi plus g of xyj. Suppose that's a conservative vector field in some open region D containing the points x sub 0, y sub 0, and x sub 1, y sub 1. And that those little functions there, little f and little g, are continuous in this region. If the vector field fxy equals del of phi xy, and if C is any piecewise smooth parametric curve that starts at the original point, x sub 0, y sub 0, and ends at x sub 1, y sub 1, and lies in that region, then yes, you can evaluate the line integral simply by plugging the terminal point into phi and the initial point into phi and subtracting. Why does that work, though? Well, let's suppose that C is given parametrically, right? The curve we're going along in this vector field is given parametrically by x equals x of t and y equals y of t. And let's say that the range of t is from a to b. So we can express the initial point as x sub a, y sub a, and we could express the terminal point as x sub b, y sub b. Now, since the vector field big F is equal to del of phi, we know that we could express the vector field big F as partial phi with respect to xi and partial phi with respect to yj. And we also note, as we have done in the previous examples in the intro, that we could easily find dx and dy in terms of t. So dx would simply be x prime of t dt, and dy would be y prime of t dt. So what does this look like when we start to substitute these things into a line integral? Well, here's the line integral structure in terms of x and y. And here's the replacement. We know the little f is partial phi respect to x, little g is partial phi respect to y. Let's now make the substitutions. Let's express x and y in terms of t, and also the differentials dx and dy in terms of t. So let's see, we would get this. Let's follow to make sure. This is all in terms of t, so t is going from a to b, so certainly the limits of integration are correct. And let's see, partial phi respect to x of xy, well, x and y can be expressed as x of t, y of t. And dx is x prime t dt, and dy is y prime t dt. So we'll just take the dt on the outside and we'll leave the x prime, y prime on the inside of these brackets. And of course here we have phi of y, right? Partial phi respect to y of the same point, x of t, y of t. So all we did to go from here to here is make the substitutions that we described up top. Now, since partial phi respect to x is little f and partial phi respect to y is little g, and since they're continuous, we can apply the chain rule here. The chain rule structure, perhaps you recall seeing it, maybe it didn't look like this. Instead of having a phi here, you had a z, but you talked about derivative of z with respect to t. Let's talk about derivative of phi with respect to t. If we did that, what we can do is take the partial of phi with respect to x, then multiply that by how much x is changing, or dx dt, which we're writing here as x prime of t, plus the partial derivative of phi with respect to y times y prime of t. That's a chain rule structure. But you'll notice that this is incorporated into our line integral expressed in terms of t. So really what we have here is an integral of something that's being differentiated. So all this integral that we talked about before is really integral from a to b of d dt of phi with respect to t. And of course, what does that mean? It means you could use the fundamental theorem for integrals that you learned in single variable calc. The antiderivative of a derivative, well, using that fundamental theorem, just plug in the top, the upper limit, plug in the bottom limit, and subtract. And it's as simple as that. So we have established a nice shortcut. We've proved how we could use this shortcut only when you have conservative vector field and you're evaluating line integrals in a conservative vector field. And remember the power of this theorem. Since C was any smooth path between two given points, as the theorem said initially, it was any path, any curve C. This really does show us that the value of the line integral of a conservative vector field along a piecewise smooth path is what we say to be independent of path. That means the value of the integral doesn't depend on the actual path that you're going along, but it depends on the endpoints. So for conservative vector fields, it's common to express this theorem looking like this. Okay? So you have the initial point, terminal point, you just plug them in and subtract. It's that simple. So a key takeaway. If a line integral is independent of path, then the vector field must be conservative. And that's why conservative vector field is such a big deal. You do the same amount of work going from one point to another, no matter what path you choose. What a wonderful world that is from a mathematical standpoint. So we hope you enjoyed this video, and we'll see you next time.